Hello everyone. So this video I'm starting here. In this video I'm starting the new subject here, refrigeration and air conditioning. Right. The subject name here I'm going to start. One more new subject, the refrigeration and air conditioning. I'm going to start here. Observe. Right. We will start discussion on it's a new chapter, new subject. Subject name is very interesting. Also, it is right. Observe. Refrigeration and air conditioning. What the things we are going to study here? Let me first list those things. Right. What the things we are going to study here in this refrigeration and air conditioning? It is a very big subject. Lot of things are there to know, and all this concept, all these things are very interesting because it is the application of this particular subject. Is the application of which one? This is the application of thermodynamics. Thermodynamics, right? The application of thermodynamics is nothing but refrigeration of air conditioning, refrigeration and air conditioning, right? So to understand this topic in a very easy way, you should have the basic knowledge on this thermodynamics first of all. Okay, basic knowledge in the sense what is constant pressure process, temperature process, what do you mean by adiabatic process, isentropic process, what are the several relations are available in adiabatic and isentropic process like this, what is constant heat transfer, constant pressure heat transfer, constant volume heat transfer, Cp, Cv, gamma, all these are basic things are not in the thermodynamics, right? Apart from that, also you should have the knowledge on first law, second law. In the second law, two statements are there, Clausius and what is that? Kelvin Planck statement. Already, I think this statement already refrigeration few parts also there in the thermodynamics, right? But here elaborately we are going to discuss about this refrigerations. Okay. So this basic knowledge is required. Basic knowledge. If you don't have, if you are very much weak here, then I will recommend first you go. Only it will take 1 hour time. 1 hour, 1 to 2 hour maximum to revise all these things what I just told. Okay, to revise one to 2 hour maximum to study all these basic things about this thermodynamics. Or else I will also prepare one video on this basic of thermodynamics, which is required very much to understand this topic only. Right? Not thermodynamics elaborately, basic things I will if it is possible, right? So let me start this one. Refrigeration and air conditioning. Observe, two part is there. Refrigeration part is there, separate, and air conditioning part is there. They are here separate, right? So the meaning of refrigeration is cooling. Simple word I will use, cooling, right? Air conditioning also here we are cooling the air, cooling the air. Air conditioning clearly about air is mentioned. Air conditioning means we are cooling the air. Not only here we are cooling the air, but also we are maintaining the water vapor level, I mean moisture level in the Air conditioning, that is latter topic, I will discuss slowly. But here refrigerations, first part we will take about the refrigerations. So in the refrigerations, what are the topic we are going to discuss? Let me list out first, then I will discuss one by one. Right? Okay. In refrigerations, so first topic I will discuss here. What is refrigeration? What is refrigeration? So, second, what is the need of refrigeration? I will discuss. Next one, application, where it is used, application of refrigeration also I will tell. Application of refrigeration also I will tell. Several examples also I will. Next, after that, several technical terms are there. Technical terms. Terms are there. We have to study. What are the technical terms like TR, ton of refrigeration? Okay, unit of refrigeration or ton of refrigerations. COP, coefficient of performance of the refrigerations. Like this, we are going to discuss all these things. We are slowly one by one. I will discuss. Okay, these are the several technical terms we have to discuss. Next one, I will give you a small comparison. Okay, small comparison on refrigerator, heat pump, and heat engine. Right? A small comparison I will here. In the next, I will start types. Types or classification of refrigerations. Types or classifications. Okay, classification of the refrigerations. In this classifications, okay, 1 minute, guys. In these classifications, we will study what? In these classifications, we will study 1 minute. Let me delete this one. In classifications, we are going to study, okay, open air, open refrigeration cycle, open type, and closed type. Closed type. Open type and closed type. Next, again the refrigeration will be classified in the point of view of refrigerant. Here we are going to study air refrigeration, air refrigeration cycle process. Okay. Then vapor compression. Vapor compression is there. Don't worry, I am just listing out the components what we are going to discuss. Slowly observe. Absorption is there. Absorption refrigeration cycle. Next, thermoelectric is there. Thermoelectric refrigeration cycle. So these are several refrigeration cycles we are going to discuss, right? After that, most important, refrigerant and its properties. Okay. After that, we will go to the air conditioning part. Okay, air conditioning part. Minimum to discuss this all these topics clearly, minimum 30 hours is required. Remember, this much only minimum. Numerical also there. 30 hours minimum is required to complete all this topic. And problem also there, numerical also there. We have to solve, right? So first I will tell what is refrigeration here. I know you know, everybody knows. Simply, the meaning of refrigeration is what? The meaning of refrigeration Refrigeration is what? Simply some cooling. But but in the interview, if somebody will ask what is the refrigeration, right? You have to give some technical definitions. This is just general definitions, right? Technical definitions. What is the technical refrigerations? We are doing cooling. So while we are doing cooling, we are maintaining the temperature of a space or a region or a body, right? Space or region or body below below the below the atmospheric temperature. Like this definition you need to give. Maintaining the temperature of a space or a region or body below the atmospheric temperature. Below the atmospheric temperature is nothing but cooling effect or not cooling. We are doing the cooling. So this is the meaning of refrigeration, right? So why it is called refrigeration cycle? Why it is called a refrigeration cycle? So that's why to understand this is refrigeration cycle, first we need to understand what is a cycle. That is already there in thermodynamics. Okay, thermodynamics. Cycle is nothing but initial point and final point is same. Initial point and final point is same. Here the meaning is very clear that this refrigeration or this cooling effect is achieved mm, by undergoing several processes. By undergoing several processes. Again, sir, what is the processes? I told that's why thermodynamics is very important. Several processes. Processes may be constant temperature processes, constant pressure processes, may be adiabatic processes, may be isentropic processes, may be constant volume processes. All these processes may be involved here. Maybe, not sure, may be involved here. Like this. Okay, so how this refrigeration effect or refrigerating effect or cooling effect will be produced? It will be produced maybe by undergoing the several process. These several processes, if will connect with each other, it will constitute a cycle, right? It will constitute a cycle. If the several processes I will connect in a perfect manner, back to back, it will constitute a cycle. That's why it is called a refrigeration cycle, right? It is called a refrigeration cycle. Meaning is what? Meaning is achieving the cooling effect, achieving the cooling effect by passing in the several processes, and those several processes will be constitute a cycle here, right? Simple meanings are not so difficult here, right? This is the meaning of refrigeration cycle, right? Okay, I think I saved. Okay, no need to save. Control N, new slide. So refrigeration cycle. This is, sir, what is the need right now? What is the need of refrigeration? Without refrigeration, nowadays, because of this global warming, very difficult to survive. Okay, whether it is a human being, okay, whether it is a human being, human being, or food items, medicine items, cold drinks, everything, very difficult to survive. Okay, now food also damaged, very issue. Medicine also expired, very damage also very issue. Cold drinks also not feeling so tasty if it is not cooled, right? That's why need of refrigeration is what? For comfortability, comfortable life everybody wanting or not. For that you need to do the job, and for doing the job you have to study the refrigeration subject. Not only refrigeration subject, every subject you have to study. Comfortable life, refrigeration is necessary. Refrigeration is necessary. Okay, necessary. Not only that, Not only that one, but this food storing purpose. Okay. Nowadays, big cold storage plant is there or not? Why, sir? Cold storage plant because of nowadays production is less. Production of the food is less. Potato, tomato, okay, vegetables production is less because of this global warming climate. They are going to waste very soon. So to keep it, to preserve it little bit more days, few more days, we need the refrigeration process, refrigeration, right? This is the need of refrigerations here. Next one, applications. Just here also I told the applications. What is the applications? In home we are using. Okay. Okay. In home we are using the refrigerations for cooling purpose. Next, refrigeration. I mean refrigerator is the one applications. Cold storage plant. Just I told. Cold storage plant. Where is the next? In medical sector also you are using. ICU is there or not? ICU is there or not? Medical sector we are using. Several industries also here using industries. Okay, in industries. Okay, ice production plant, which is ice plant. They're also using. Okay, ice plant. They're also using. Like this, a number of applications we are going to get. Okay, this is called application of the refrigeration cycle. Right, application of the refrigeration cycle. Next, I will talk about several technical terms here. What are those technical terms? I mean, I can say those are the properties, one properties also. First one is a TR, ton of refrigeration. It is short form is TR, ton of refrigeration. Right? Ton of refrigeration. This is also called, this ton of refrigeration is also called unit. Unit of refrigeration. Okay, unit of refrigeration. Okay, what is the unit of refrigeration, sir? To measure the refrigeration quantity. To measure the refrigeration quantity, we need the unit. Not only refrigeration quantity, any physical quantity you want to measure, you want a unit or not? Mass. For mass, kg is required. For length, meter is required. For time, second is required. For force, Newton is required. Like this, to measure this refrigeration quantity, unit is required. Unit is what? DR. Okay. It is a derived unit or a predefined unit. It is a derived unit, right? Derived unit. Derived unit. Okay. What is this TR? Full form? Ton of refrigerations. Okay. So, ton of refrigeration. So, we are very much acquainted with this one. kg, length, second, Newton, watt, kilojoule, like this. And what is this TR? You know, TR is nothing but, this is TR is nothing but we can convert this TR into kilojoule term, kilowatt term also. There is a relations. Okay, we can convert this TR into kilojoule term and kilowatt term. Right? Observe slowly. I will tell how to convert this TR because TR naming is little bit different other than these units. But no problem. We can convert this TR into kilojoule per month or a kilowatt per month. Then it will be easy. How to convert? Observe. First, to convert it. First, I need to know the definition of the TR. Sir, unit having also definitions? Yes, but this ton of refrigerations, it is having one small definition, small as well as very beautiful definition also. Observe. What is a TR? Okay, this is a very common question, right? In semester exam also, bit questions, small 2 mark, 3 mark questions are there. It is what is meant by TR or defined TR. Very simple. Okay. It is defined as, right? It is defined as uniform melting of 1 US ton, not only 1 ton. 1 US ton of ice, right? 1 US ton of ice from from and at 0 degrees Celsius in 24 hours. In 24 hours, right? It is defined as the uniform melting of 1 US ton of ice from and at 0 degrees Celsius in 24 hours. Right? From these, I can convert TR value to kilojoule format or kilowatt format. Observe. What is the meaning? 1 TR value is what? 1 US. Sir, what is this 1 US ton? Generally in India, 1 ton value is what? 1 ton value is this 1,000. But in US ton, this is not exactly 1,000. This is 900 something. I think 918 like this. Like this value will come. But in India, 1 ton value is 1,000. But in US, 1 ton value is not 1,000. That's why exclusively we have written US ton value. So why this US ton particularly used? Because this concept is developed by in US only, not in India. Refrigeration concept, okay na? Those concept is developed in US only. That's why based on their scientists, those scientists developed those concepts, so they have written as per mm, their I mean quantity, they have written 1 US ton there, right? So 1 TR is equal to what? Suppose I will derive by considering this 1,000. Okay, 1,000. First, let me derive by considering only 1 ton means 1,000. What is this one? 1 TR equal to, okay. And one more thing I want to say here. Here, one concept is required: latent heat. Latent heat. Okay, latent heat is meaning is what? Latent heat is meaning is also called hidden heat. Hidden heat. Okay, hidden heat, right? 1 T, hidden heat or latent heat. So how many types of heats are there? Okay, let me explain that one also here. Also. So generally, heat are two types. One is sensible heat, another is latent heat. What is this one? Observe. Slowly observe, I will tell. So this is my work. Okay. Okay. This is my y-axis. Take this line. Okay. This is my y-axis. Right. And this one is the x-axis. The x-axis. Right. Now, suppose this is the temperature, and here any parameter. Suppose x is the parameter here. X, any parameter I am taking. X parameter. What I am doing here, I am taking a transparent jar. transparent, made up of glass, transparent. And in this jar, I have given here, suppose burning facility, heat I am providing here. This is a lamp, burning will be done here. Continuously it will be supplied. This is a transparent container. Inside the container, I am keeping a piece of ice, 1 kg ice. Okay. 1 kg ice I am keeping here. Baraf ke gole, right? What is the mass here? 1 kg, right? Continuously I am supplying here heat. Okay. Observation has to be done here. I have to observe here. Observe. Now, observer is observing here. Right? He is observing. One minute. He is observing here. So, what observation? Let the temperature. Here also, I am attaching a thermometer. Thermometer is there. A thermometer is also there. This is called thermometer. This one. Now, when heat is not there, let the temperature, just assume, let the temperature is minus 5 degrees Celsius. Just I kept the fresh cube here. The temperature is minus 5 degrees Celsius. This is temperature column or not? Yes. Minus 5 degrees Celsius. Now heat started. Heat started. Here temperature also showing minus 5 degree in the thermometer also. Temperature measuring instrument here also showing minus 5 degree. Now heat supply started, continuously started, but I will not stop the heat supply. Continuously it will be started. What will be happen? Observe. Slowly temperature will be rising, minus 5 to minus 4, minus 3, minus 2, minus 1. Like this, the temperature will be rising. Then 0. Then it will come 0. It will come 0. See, minus 5, minus 4, minus 3, minus 2, minus 1. Then here 0. Right? So, if I draw the graph here up to 0, it will go like this, straight line. Go like this. Right? Heat is supplied continuously here, heat is supplying here, continuously heat is supplying here. The temperature slowly increases, minus 5, minus 4, minus 3, minus 2, minus 1, 0. Once a 0 degree will be reached, okay? Once 0 degree will be reached, for certain period of time, the temperature increase will be stopped here. At 0 degree, for certain period of time, the temperature increase, increase of temperature will be stopped here. At 0 degree, will stop here. But continuously, I mean, adding the heat. No doubt, we know when heat will be added, temperature will be increased. But that increase in temperature will be reflected here for minus 5, minus 4, minus 3, minus 2, minus 1. Once 0 degree will be reached, the increase in temperature will be stopped for a few moments. Sir, up to what moments? Up to what moments it will stop? Until all this ice particle will be converted to, until all the ice particle will be converted to liquid particle. Right? All the ice particle will be converted to liquid particle. Till that time, there is no change in temperature, whereas continuously I was adding the heat. Whereas continuously I'm adding the heat, but there will be no change in temperature. The reading of the thermometer will be fixed, stop at this that particular at a particular level for a few moments. Up to which moments, sir? Up to what moments? Up to all these solid particle, ice is the solid state now. Solid particles will be converted to liquid particles, all 1 kg, that all 1 kg will be converted to liquid particles. Now if I draw the same situation in the diagram, what will be happening? Temperature after 0 degree, some heating process is going on, but what happened? Temperature not increase. Temperature is constant for a few minutes. See, temperature I show constant or not? Here 0, here 0, here 0, everywhere 0. For this moment, temperature not changed. Again, suddenly, once all particle is converted to liquid here, again suddenly temperature will be start rising. In the thermometer, again 1, 2, 3, like this it will rise. 1, 2, 3, 4, 50, 60, 80, 90, 100, up to 100 degree it will rise. Continuously heat also added and temperature also rise. But only for this 0 degree period until the all solid particle is not converted to liquid particle, temperature just become hanged. It will not show any reading, it will not change its positions for that particular moment. That's why that particular movement also I have recorded in this graph or not here. Constant temperature. Now again, once the liquid particle is converted to all the solid particle is converted to liquid, again temperature will start increasing. That means again temperature slowly increases up to 100. Right? This is the 100 line or not? This is 100 line. Once again at this 100, this is 100 suppose, at this 100 again my temperature will become hanged. No reading change, no reading change. Sir, for that when it is reached at 100 degree, once again my thermometer will not stop. My thermometer work will be stop. It will not change the reading. Sir, until what time? Until all the liquid particles here right now is converted to gas particles, right? All the liquid particles, 1 kg liquid particles, until it is converted to gas particles, it will not change the temperature reading. It will remain at 100 degrees. So that value also I'll record in the graph. Again at 100, the temperature is constant, right? Temperature become constant. Now, once the all particles will be converted to gas particle, 1 kg liquid particle is converted to gas particle. Suddenly, my temperature thermometer will work after 100, 101, 102, 103, 104, 105, 200, 300, 400. Like this, it will be gone. That means again temperature rise here. So totally this experiment I have recorded in this graph, right? I have recorded in this graph. Whatever happening here with the temperature, based on that I record the temperature at several times, several points. Observe from -5 degree to 0 degree temperature changing. Okay, for particular period of time temperature changing. At 0 degree temperature again fixed for particular time period, for a certain time period, 0 degree constant. Again after 0 degree, once all the particle converted to liquid particles, again temperature changes. Observe temperature changes or not? Temperature increases. Again at 100 degree temperature again become fixed constant. up to until all liquid particle converted to gas particles. Then after that, once it is converted to gas particle, again temperature increase, right? So two situation I am getting here. Sometimes by adding this heat, but heat addition continues here. I have not supplied this, I have not stopped the supply. I have not even stopped the supply for a single second also, right? Heat addition continuously we are giving here. So two situation here arising. What? Sometimes temperature with heat addition, temperature is increasing, and sometimes even if heat also added continuously, temperature is not increasing. Okay. Sometimes with heat addition, temperature increasing, and even sometimes with addition of heat also temperature not increasing. So that portion clearly here I differentiate. What is that portion, sir? What is that portion? Observe that portion with heat addition, temperature changes here to here, and with heat addition, temperature not changes here to here. Again, with heat addition, temperature changes here to here. Again, that means here to here, right? Here to here. I'm showing in the down. Again, again with heat addition continuously going on, but temperature not changes here to here. Blue line not changes, red line changes. Very danger. Again, changes here to here, right? Okay. Here to here changes. No, what we are calling to these portions? This portion, this red line. It is called sensible heat. It is called sensible heat. Sensible heat. Why the name is? Because very much sensitive to temperature is very much sensitive to heat. Once heat changes, temperature also changes. Heat increase, temperature increase. Heat decrease, temperature decrease. That's why sensible heat. But those blue lines, this line and this line is called latent heat. It is called latent heat, or one more name is there, hidden heat. Hidden heat. Okay. Heat is hiding, no reflection in temperature, no changes in temperature. Heat is continuously supplied. This is the concept of latent heat and hidden heat. You know what is the value of this latent heat? That means continuously from here to 0 degree to 0 degree, we are adding heat but no temperature. For this 1 kg ice, for this 1 kg, what is the mass? 1 kg or not? Then the value is calculated during this period. During this period, how much heat we are giving here? How much heat is we are giving here? 3, 3, 5 kilojoule per kg. Kg of mass is there. Nice. If it is 2 kg, then into 2. If it is n kg, then into n. At currently 1 kg, so 335. Observe, for this latent heat period up to here, heat is continuously added, but temperature not changes. So how much heat is adding during that period? 335 kilojoule per kg. Similarly, in this period, also temperature not change. This is also latent heat. So how much heat is added here? 2260 kilojoule per kg. Okay, if this much heat will be added, okay, observe, if this much heat will be added to 1 kg ice, then what will happen? All solid particle will be converted to liquid particle. And if this much heat will be added to the liquid particle, then what will happen? All liquid particle will be converted to gas particle and then vapor particles. Right? These things is happening here. Then this is called latent heat of ice. This is called latent heat of steam or water, we can say. Latent heat of vapor. Latent heat of vapor. Very more correct, right? Latent heat of vapor is 2260. Latent heat of ice is 335. Unit is what? Kilojoule per kg. Right? Now observe. Observe, sir. Observe here. Control N. Uh, 1 TR, we're talking TR. 1 TR. Definition I have written. What is the definition? 1 US ton. I will take 1 ton. Later I will take 1 ton. 1 ton of ice. Sir, for 1 kg ice, what is the latent heat? 335. No? 335 for 1 kg ice. 335 kilojoule per kg for 1 kg. Now 1 ton, how much kg? 1000 kg. Then what is the latent heat? 1000 into 335. Okay, 1000 into 335. This much latent heat will be there. Okay, this much latent heat will be there. Sir, this total experiment is conducting how much time? 124 hour. I have written a 24 hour in from and at 0 degree Celsius in 24 hour. Definition is very important. 24 hour. 24 hour is nothing but, can I write 24 into 60 minute? Can I write again into 60 second? Yes or no? Definitely 100% I can write. Okay, na? So this is, if I'll solve this one, I will get the answer. What is the answer I will get, sir? What is the answer I'm going to get here? This is called, oh sorry, this is hour, 24 hour. It is converted to minute, 60 minute. Then if I'll multiply 60, then I will get second. Okay, I'll get second. So if I'll solve this one, I will get around, okay, let me 1 minute, guys. Let me remove this 160. Let me minute. I'll keep it 24 into 60. 24 in 24 hour into 60. 1 hour is 60 minute. 1 hour 60 minute. So 24 hour 24 into 60 minute. Okay. If I'll solve this one, how much answer I will get? How much answer? Around 227 kilojoule per minute. Kilojoule per minute. Sir, how sir kilojoule per minute? Observe. 1000 kg na kg 335. What is the unit here? Kilojoule per kg. So unit is kilojoule per kg. Now at the below 24 hour into 60 I converted to minute. Now kg cancel. Kilojoule per minute they are not. So kilojoule per minute. Okay, kilojoule per minute. But in the definition there is 1 ton or 1 US ton, 1 US ton, and 1 US ton value is not 1000. It is 900 something. In place of 1000, if I'll put suppose 910, this 227 value decrease or increase? It will be decreases. It will come around 210 kilojoule per minute. So this is the standard value. 1 TR equal to, as per the US standard, 1 TR value equal to 210. As per Indian standard, 1 TR become 227 kilojoule per minute. Okay, but this is not followed. This value is not followed because everything they have designed by the help on the basis of 1 US ton. Okay, so this value I have to follow 210 kilojoule per minute. Okay, again if I'll simplify this one, 210 kilojoule per minute. Okay, now again if I'll multiply here 60, okay, 60, that means divided by 60, it will become 3.5 kilojoule per second, is nothing but 3.5 kilowatt, right? So one TR value is 3.5 kilowatt. Sir, why you are converting to kilowatt, kilojoule per minute? While you will solve the problem, okay, unit conversion will be required there. Unit conversion. That's why you need to know 1 TR value equal to 210 and 1 TR equal to 3.5 kilowatt. Okay, this is the 1 TR definition and mathematical expressions, right? Okay, so observe. Next is what? COP. Next is what? COP. Okay, COP. Full form, coefficient of performance, right? Coefficient of performance. What is the meaning of coefficient of performance? You know, there is a term we are using frequently: efficiency, efficiency, efficiency. Okay, suppose, okay, let me explain this one also, no problem. So, this is the heat engine. Suppose. What is this? Heat engine, turbine, IC engine, okay, bike engine, those are heat engines, right? Heat engines. Here we are supplying heat. By burning of fuel, we are supplying heat Q1. Okay. And by burning of fuel, by supplying heat, we are getting some work here, W work. So that a vehicle is moving from one place to another place. Right? But actually this one is what? Violating the second law. Because with one reservoir, what is the Kelvin Planck statement? With one reservoir, we cannot design the heat engine. So definitely heat rejection will be there or not through the silencer pipe. Silencer heat will be rejected and heat rejection is acute. This is rejection side or okay, rejection side, and this is feeding side. Feeding. It is feeding here. Or a technical term we can use. This is a source. Technical term. This is source, and this is called sink. Okay. So W is, so what is the efficiency of this heat engine right now? How the efficiency is calculated? Efficiency is calculated. So what output we are getting and what input we are giving, right? What output we are getting and what input we are giving. In this particular figure, sir, what is the output? This one is the output. And what is the input? This one is the input. Yes or no? Sir, you will tell, sir, this one also output because see arrow mark gives no, this is not output, right? This is not out. Output is only W. Input is what? Q1. Input is Q1. If I will simplify this one, then I have to put first law of thermodynamics here. First law of thermodynamics. If I will simplify this one, what is the first law of thermodynamics? Net heat transfer equal to net work transfer. Observe, net heat transfer. Net heat transfer, sir, Q1 is one heat transfer and Q2 also one heat transfer. And this side only W is there. Sir, here plus sign or minus sign I will put. Here plus sign or minus sign. Remember, when heat is supplied to the system, it is positive. When it is rejected, it is negative or not. So now here heat Q1 heat is supplied to heat engine, positive. And Q2 heat is rejected from the heat engine, minus. Right? Q1 minus Q2. So W equal to Q1 minus Q2. Can I write here equal to Q1 minus Q2 divided by W? Sorry, Q1. Simplification, more simplification. Again, if I'll simplify, sir, Q1 by Q1 minus Q2 by Q1. Again, 1 minus Q2 by Q1. This is the efficiency of the heat engine. Right? Efficiency of the heat engine. Everybody know. You know. I know. Everybody know. Right? Observe. What is my next here? Sir, There is one more device, refrigerator is there, right? Refrigerator, refrigerator. So what is the function of the refrigerator? What the refrigerator for cooling purpose, for cooling purpose, right? Oh, this is the body. Arre, arre, arre. Okay, one. Hmm. Acha. This is the refrigerator body inside. Okay, so I'll connect here like this, and this is the outside of the refrigerator. Outside. This is inside, inside, and this is outside. Okay, so outside also I connect. Inside means okay, inside of the refrigerators. Outside means backside of the refrigerators, right? Backside. What will be happen, sir? From inside, refrigerator will be extracted. From inside, heat will be extracted. Okay, you are storing some items, food items, vegetable items, drink items, cold drinks only, right? Cold drinks. Water also there, milk also there. Like this, you are storing here inside. Then from the inside, because you are bringing those items from the atmosphere, from the market, and you are putting it inside the refrigerators. So what will happen? Those items has to be released heat. So heat will be extracted here. It will be, once the heat will be extracted, that heat will be go where? It will go to thrown to outside. Okay, the refrigerator work is it will be take heat from the inside and throw to outside automatically, or something is required. Electric power is required or not? Electric power is required. Automatically, it cannot do. Automatically, it cannot take heat from inside and throw to outside until electric current is not there. It will not work, right? Electric current is nothing but how the electric current we are getting from mechanical work or not. That means work we have to supply. Work we have to supply. Observe. Let Q1 amount of heat is taking from inside, and Q2 amount of heat it is throwing to outside. Right? Q2 amount of heat is throwing to outside. Sir, what is the efficiency in that case of the refrigerator? What is the efficiency in that case in place of refrigerator? Sir, what is the efficiency in case of heat engine? Sir, output by input or not? Here, observe. Here, observe. Sir, what is the output here? What is the output in this case? Sir, don't judge output from this arrow mark. Sir, arrow mark is away means output. No, arrow mark is in means input. No. Output here nothing but what is the requirement? What is the requirement? Here in the heat engine, which one is the requirement? W is the requirement or not? Yes. W, heat engine we are using to produce some work. So requirement is work. That's why it is output. Okay. And how we are getting the output? By giving something. That is the input. Here by giving Q1. That is the input. Now observe. Here in this refrigerator, sir, which one is the requirement here? In the refrigerator, requirement is heat extraction. Cooling, requirement is cooling. Cooling is nothing but heat extraction. In the refrigerator, okay, cooling is our requirement. So heat cooling is nothing but heat extraction is the requirement. So here, what is the requirement? That is become out. And how it is extracting the, or how it is taking the heat from the inside? By supplying, by giving something. Here we are giving Q1, here we are giving W. So this is become input. Now efficiency become output by input. Here also output is Q1, input is W. But this efficiency term will not suitable for this refrigerator, but it is most suitable in heat engine. So efficiency term is not used here. COP term will be replaced, but meaning is the same. COP meaning is also output by input. Efficiency meaning is also output by input. Remember, don't confuse here, right? Both meaning is same, but the term we are using here different. Why? Reason is there. Later I will tell that one also. If I will explain that one also, it will the video will go long, more long, right? So here output by input Q1. Sir, if I will simplify this one Q1 by W, then what I need to do, I have to apply first law here. What is the first law? Summation of Q equal to summation of W. Observe, sir, summation of Q. Q1, Q1, Q2 is there, equal to W is there or not? W is there, right? Now tell me, here W, W means work. Here work we are giving or we are getting. Work we are giving or we are getting. Sir, here work we are supplying to the refrigerator. Observe RMR supply. But in this case, work we are getting. That's why work was positive. If any machine or any engine, any system producing work, that is treated as positive work. If any engine or any system consuming work, that is treated as negative work. So minus W, right? And here observe Q1 is supplying or not? Q1 is supplying. So I told na, if heat is supplied to a system, that is positive, and if it is rejected from the system, that is negative. Now Q2 is rejected from this refrigerator or not? That means Q1 minus Q2 equal to minus W. If I simplify it, W take to this side, W become Q2 minus Q1. Now here you apply Q1 divided by, in place of W, you put this value Q2 minus Q. This is the COP formula of the refrigerator, right? COP formula of the refrigerator. Okay, this is the efficiency formula of the uh, heat engine just derived before, and this is the COP formula. COP is nothing but efficiency, but notation wise the it will be changed. We are using different notation here, right? That is also reason is there. Later I will tell. Right? This is about what? CO heat engine and refrigerators, right? One more thing is there. What is that one? Heat pump. Observe slowly. 5 minutes only. Okay, heat pump is there. Heat pump. Same heat pump. This is now. This is become outside. Heat pump generally we are using in summer days or not. This is become room inside. This is the room inside and this is outside. So what will happen here? Heat will be taken from outside and thrown to inside. Okay. Heat will be taken from outside and thrown to inside of the room. Is it possible automatically? No. Again I have to give some work here. W work I have to provide. Right? Once I will give W work, what will be happen? Sir, Q1 amount heat will be taken from the outside and Q2 amount of heat is thrown to the inside. Then sir, what is the efficiency? Output by input or not? Input. Sir, what is the output? Don't judge output input from this arrow mark. Most of the students are doing like that only. Arrow mark in means towards means input, outside means output. No, output means what is the requirement here. What is requirement in the heat pump? In the heat pump, heating is required or cooling is required. Sorry, heating is required. That means output is a Q2 only. So Q2 divided by input is which one? W. Na? Oh, W is in here. Observe. Then to more simplify it, I need to apply the first law here. Summation of Q equal to summation of W. Very interesting law it is. So Q1 minus Q2, sorry, Q1, Q2 equal to W. Again, W here supplying means minus. And Q1 entering to the supplying to the HP and Q2 rejecting. So Q1 is positive, Q2 is negative. So minus sign. Here minus W. If I simplify W, Q2 minus Q1. If I'll put here, I will get Q2 by Q2 minus Q1. Once again, the efficiency term will be not suitable here. COP of the heat pump. Same output by input or not? Yes. COP of the heat pump. COP of the heat pump is what? Q2 by Q2 by Q2 minus Q1. Just before I derived, just before I derived, COP of refrigerator is what? Just before Q1 by Q2 minus Q1. Here, what is the difference? Only the bottom part. Numerator is the same. Q2 minus Q1. Here also Q2 minus Q1. Here Q1. Here Q2. That things only change. So let me simplify once again this one. Observe. Can I write this one? Q2. Q2. Q2, right? Q2 minus Q1 plus Q1. This top term, denominator. Here only Q2. Na? So what I have done, I subtract one Q1, I add one Q1. So if they will be cancelled, then Q2 will be remaining or not? Okay. Just like I have written. Now Q2 numerator same I am writing Q2 minus Q1. Q2 minus Q1. Right? Observe sir. Can I write like this? This is one term. This is one term. Okay. And this is one term. Okay, na? Sir, A plus B by C. We are writing what? A by C plus B by C. The same way. Q2 minus Q1 by Q2 minus Q1 and Q1 by Q2 minus Q1. Okay, na? See, I will write here. Here I will do. Here I will do. Here I will do. Q2 minus Q1 by Q2 minus Q1. So it will be cancelled. Plus Q1 by Q2 minus Q. So this term will be cancelled. Cancel means 0, huh? No, 1 plus. Observe what is the term? Q1 by Q2 minus Q1. Here you observe. Here, where, here. Q1 by Q2 minus Q1. For what purpose? COP of refrigerator? No. Can I write here? COP of refrigerator. That means this is COP of heat pump, right? COP of heat pump is equal to is equal to is equal to 1 plus COP of refrigerator. This is the derivations, right? So what I got here? COP of HP heat pump equal to 1 plus COP of RE. 2 mark question will come. Okay. 2 mark question, small numerical will come in on this. Okay. In competitive exam also this concept will be there, right? This is what I discussed today in this video. I discussed what is refrigerator, its need, its applications, right? Its applications we have several technical terms like TRs and COP. Then I discussed about heat engine and refrigerator and heat pump. Again, latent heat and sensible heat. Okay, all these things I covered in this video. Right? You slowly observe, slowly see the video and try to make the notes. In the next class, next video, I will start what refrigeration cycle types of refrigeration cycle in the next video I discuss. So I conclude here, guys. Please take care and bye.